There is a single calculation sitting in a physics paper somewhere that is wrong by a factor of 10 followed by 122 zeros. That is more zeros than there are atoms in everything you have ever seen, every star in every galaxy, every grain of sand on every beach on Earth. The biggest miss in the history of science. The calculation is a prediction about the energy of empty space itself, the vacuum, the nothing between the somethings, and here is the part that should make you sit up. The exact same theory that gets the energy of empty space catastrophically wrong can also predict how a single electron behaves to 12 decimal places of accuracy. That is like measuring the distance from New York to Los Angeles and being off by less than the width of a single human hair. The same equations, the same machinery, the same physicists using the same chalkboards, right by an absurd amount in one place and wrong by an even more absurd amount in another. The theory is called quantum field theory, and something very strange is going on inside it. Because if it is just a surface layer sitting on top of a reality we've never directly seen, then what exactly is underneath it? Get comfortable, hit subscribe if you have not, and stay with me. Because what physicists are quietly figuring out about this contradiction might change what reality even means. Part 1. The 2025 moment physics stopped looking for a crack. For more than 2 decades, the muon G-2 experiment was the closest thing physics had to a smoking gun. Scientists at Brookhaven National Laboratory had measured something strange about the muon, the heavier cousin of the electron back in the early 2000s. The muon's magnetic behaviour, the way it wobbled in a magnetic field, did not quite match what the standard model predicted. The discrepancy was small, about 2.5 parts per million, but in a field where agreement is usually exact to many decimal places, even a tiny mismatch is electrifying. Physicists looked at that gap and they saw a doorway. A door cracked open just slightly, and through it, possibly, lay an entire unseen universe of new physics. Supersymmetry, the long-awaited theoretical extension that would double the particle content of the universe. Hidden particles that interact only weakly with the matter we know. New forces beyond the 4 we have already catalogued. Dark sector physics that might finally explain the 27% of the universe that seems to be made of something we cannot detect directly. All of it could potentially squeeze through that small 2.5 parts per million crack. So when Fermilab took up the experiment in the 2010s, upgrading the apparatus and importing the giant 50-foot magnet ring all the way from Brookhaven by barge and truck, the entire physics community held its breath. The first Fermilab results came in 2021 and they confirmed the anomaly. The world went a little wild. New York Times articles, press conferences, theorists scrambling to publish papers explaining what kind of new physics could be lurking just out of view. Then came 2023 with more data and tighter error bars. The anomaly held. By 2024, the experiment had collected so many muon decays that the statistical uncertainty was the smallest it had ever been. And then in 2025, the final results dropped. Combined with updated lattice quantum chromodynamic simulations, computer calculations of the strong force contributions to the muon's magnetic moment, the gap closed. It just closed. The standard model prediction and the experimental measurement now agreed within their combined uncertainties. There was no anomaly anymore. There was no doorway. There was just one more case of the standard model being right, again, in the most boring possible way. The press releases used words like triumph and confirmation. But if you looked at the faces of the physicists, if you read between the lines of the technical papers, you could feel something else underneath. A kind of quiet exhaustion. Because this was supposed to be the moment. This was supposed to be the experiment that finally cracked the egg, and instead, the egg got harder. 20 years of anticipation collapsed into a graph showing 2 error bars that overlapped almost perfectly. Nothing new was discovered, only better agreement. And here is where the deeper unease creeps in. Every time physics expects failure, the theory becomes more stable. every time we think we have caught the standard model in a contradiction, the contradiction evaporates? At what point does stability stop looking like success and start looking suspicious? At what point do you start to wonder whether the problem is not missing physics, but physics that is somehow too perfect? Because if quantum field theory is supposed to be incomplete, and we know it must be, since it does not include gravity, and it does not explain dark matter, and it does not predict the cosmological constant, then why does it keep passing tests it should be failing? That is the puzzle we're going to live inside for the next several thousand words, and it points toward an answer that physicists have been circling around for decades, but have only recently started to take seriously. The idea that quantum field theory might not be a fundamental description of reality at all. It might be a stable surface layer, an effective skin stretched over something deeper, and the reason it never breaks is not because it is the truth. It is because it is so high above the truth that the truth cannot reach up and disturb it. So what was the muon experiment really probing in the first place? And why did closing this particular crack feel so much heavier than just one more failed search? Part 2. What the muon anomaly was really about. The muon is one of nature's strangest gifts to experimental physics. It looks exactly like an electron in almost every way. Same charge, same spin, same response to electromagnetic forces. The only meaningful difference is mass. The muon weighs about 207 times more than the electron, which makes it both heavy enough to feel certain quantum effects more strongly, and short-lived enough that it decays within a couple of microseconds. That tiny window of existence, just enough time for the muon to wobble a few thousand times in a magnetic field, turns out to be one of the most sensitive probes of unknown physics ever invented. Here is why. When a charged particle with spin sits in a magnetic field, it precesses. It wobbles like a top. The rate of that wobble depends on what physicists call the G factor, and for a perfectly classical point particle, G would be exactly 2. But quantum mechanics ruins the simplicity, because the vacuum around the muon is not actually empty. Empty space, as far as quantum field theory is concerned, is teeming with what we call virtual particles, pairs of electrons and positrons popping in and out of existence, photons fluctuating in and out of nothing, quarks and antiquarks briefly appearing, interacting and vanishing again. All of these vacuum fluctuations leave their fingerprints on the muon as it wobbles. They tug on it, they push back against it, they slightly adjust its magnetic response. The total effect shifts the G factor away from 2 by a tiny amount. That tiny shift is G-2, and because the muon is heavier than the electron, it interacts more strongly with these vacuum fluctuations, especially fluctuations involving heavier or more exotic particles. If there were any unknown particle out there, anything not described by the standard model, the muon would feel it more strongly than the electron does. Measure G-2 precisely enough, compare it to what the standard model predicts, and any disagreement is essentially a window into the otherwise invisible vacuum. For most of the 21st century, that window seemed to be cracked open. The Brookhaven measurement and the early Fermilab measurements all suggested a value slightly higher than what the theorists were calculating. The gap was small but persistent, and it kept showing up in independent experimental runs, which is exactly the sort of stubborn reproducible mismatch that historically signals real new physics. But the calculation side of G-2 has always been a nightmare. The hardest part is what physicists call the hadronic vacuum polarization. That is the contribution from quark and gluon fluctuations, the strong force pieces of the puzzle, and the strong force is brutally difficult to compute from scratch. For decades, the standard approach was to use experimental data from electron-positron collisions to estimate the hadronic contribution indirectly. But starting around 2020, a different method, lattice QCD, where you simulate the strong force on a giant computer grid representing space and time, started producing more precise results, and the lattice results suggested the older estimates had been slightly off. By 2025, multiple independent lattice groups had converged. The theoretical prediction shifted, the experimental prediction stayed roughly where it was, and the gap closed. So what would new physics have actually meant if the gap had stayed open? It could have meant supersymmetry, the theoretical framework that pairs every known particle with a heavier superpartner, was real, with the superpartners contributing to vacuum fluctuations the muon could feel. It could have meant the existence of a whole hidden dark sector, a parallel zoo of particles interacting with our world only through tiny couplings. It could have meant new force carriers, new heavy bosons, new generations of leptons. It would have been the experimental smoking gun that the Standard Model was incomplete in a specific, accessible, measurable way. Instead, the smoking gun turned out not to be a gun at all, just a shadow on the wall, and here is the part that connects back to where we started. Quantum field theory was not falsified, it was not weakened, it was not pushed into a corner. If anything, it was reinforced. The Standard Model swallowed the most carefully constructed challenge of the last quarter century and came out the other side without a scratch, which would be cause for celebration if quantum field theory were a complete theory of nature. But it is not. We know it is not. So why does it keep behaving as if it is? Part 3. A theory that refuses to break. The muon result is not an isolated case. If you zoom out and look at the entire history of modern particle physics over the last 40 or 50 years, the pattern is impossible to ignore. Anomaly after anomaly has appeared, attracted attention, generated theoretical excitement, and then quietly resolved in favour of the Standard Model. The most spectacular example was the Higgs boson. For decades, the Higgs was the missing piece. It was the particle the Standard Model required to explain why other particles have mass, and it had never been observed. Whole generations of physicists built careers around the search for it. Whole accelerators were designed around finding it or not finding it. When the Large Hadron Collider finally turned on in 2008, one of its primary missions was to either discover the Higgs or to prove it could not exist at the energies the Standard Model predicted. In 2012, after years of running an analysis, the announcement came. The Higgs was real. It existed at almost exactly the mass theorists had calculated. The Standard Model was complete. Every particle it predicted had now been observed. Then there were the neutrinos. For a while it looked like neutrinos might break the Standard Model wide open. The original theory said they were massless, but experiments in the late 90s and early 2000s showed that neutrinos oscillate between different types as they travel, which is only possible if they have mass. This was a real anomaly. A genuine extension of the Standard Model was required, and yet the extension turned out to be small. You add a tiny mass term to the neutrino sector, you account for the oscillations, and the whole framework continues to work. The basic structure of quantum field theory was not threatened. The neutrino mass story is a footnote, not a revolution. There have been smaller anomalies too. The proton radius puzzle, where measurements seem to disagree about the size of the proton. Various flavor physics anomalies in B meson decays, where certain rare processes look like they might be deviating from predictions. Hints of new particles at colliders that excited everyone for a few months before vanishing in better data. Almost without exception, the anomalies have been resolved on the side of the Standard Model. Better measurements, better calculations, deeper analysis, and the theory keeps holding. There is no confirmed violation of quantum field theory predictions at any energy any human-built collider has ever reached. Think about that for a moment. We have been smashing particles together at ever higher energies for over a century. We have built bigger and bigger machines specifically designed to break our current best theory and force us to write a new one. And the theory just keeps absorbing whatever we throw at it. There is something philosophically unsettling about that. What kind of theory never fails? In the rest of science, theories fail constantly. That is how science progresses. Newtonian mechanics failed at high speeds and gave us relativity. Classical electromagnetism failed inside atoms and gave us quantum mechanics. Even general relativity is expected to fail at the centers of black holes and at the moment of the Big Bang. Failure is the way we discover the next layer down, but quantum field theory, in its specific application as the Standard Model of particle physics, has not failed within the energy ranges we can directly probe. It has only succeeded, again and again, sometimes in ways that defy the limits of measurement itself. So we are in this strange position where physics is not discovering chaos. It is discovering consistency. Layer after layer of consistency. Test after test of consistency. And the more consistent the theory turns out to be, the more it starts to feel like a theory that knows something we do not. Like there is a structure underneath it that is responsible for the consistency, and the theory is just describing the surface effects without actually touching the cause. Which brings us to the most extreme example of this consistency. The calculation that more than any other made physicists realize they were dealing with something almost impossibly precise. The 12 decimal place miracle of the electron itself. Part 4. The 12 decimal miracle. Let me try to give you a sense of just how absurd the 12 decimal place agreement actually is. The quantity we're talking about is called the electron's anomalous magnetic moment. It is the same kind of measurement we just discussed for the muon, except for the electron. The experimental and theoretical work has reached a level of precision that has no real comparison anywhere else in human knowledge. The current measured value of the electron's G-factor agrees with the quantum field theory prediction to roughly 1 part in a trillion. To put that in physical terms, imagine measuring the distance across the entire continental United States, from the Atlantic coast of Florida to the Pacific coast of California, about 3,000 miles. A trillion is 1,000 billion. So 1 part in a trillion of 3,000 miles works out to a width smaller than a single human hair. That is the kind of agreement we're talking about. You take the most fundamental theoretical framework in particle physics, you crank it through a calculation that involves summing thousands of quantum effects, and the answer matches reality to within the width of a hair across an entire continent. There is nothing else like this. In biology, agreement between theory and experiment within a factor of 2 is often celebrated. In chemistry, precise measurements might reach a few parts per million. In general relativity, the most precise tests, like the binary pulsar timing or atomic clock comparisons in different gravitational fields, reach maybe 1 part in 10,000 or better. Even those, impressive as they are, fall short of 1 part in a trillion by orders of magnitude. The electron's G-factor is not just precise, it is precise in a way that almost feels unfair to the rest of science, and it is not the only example. The Lamb shift, which is a tiny adjustment in the energy levels of the hydrogen atom caused by the electron interacting with the vacuum, was measured precisely in the 1940s and matched quantum electrodynamics to several decimal places, and the agreement has only improved since. The Casimir effect, where 2 uncharged metal plates placed close together in a vacuum experience a measurable attractive force purely because of vacuum fluctuations between them, has been verified experimentally with high precision. Every prediction quantum electrodynamics makes about the electromagnetic interaction has been confirmed to extraordinary accuracy. And here is the way the calculations actually work, because this is where it starts to get strange. The technique is called perturbation theory. You write down the simplest possible interaction between an electron and a photon, the basic vertex, and you calculate it. Then you add a correction by considering more complex processes. The electron emits a photon, which turns into an electron-positron pair, which annihilates back into a photon, which the original electron then absorbs. That is a more complicated diagram, called a one-loop correction, and it makes a small adjustment to the simple answer. Then you go to 2 loops, with even more complex internal vacuum fluctuations, then 3 loops, then 4. Each level of correction is harder to calculate, involving thousands or millions of individual diagrams that have to be added up. By the time you get to the level of precision needed to match the modern experimental measurement of the electron's G-factor, you are calculating 5-loop contributions, which involve mathematical structures so complex that single calculations can take years and require armies of physicists and supercomputers. The astonishing part is not just that the calculations can be done, it is that each new loop level produces a smaller correction than the last, and the corrections converge toward the experimental value. The series behaves itself. The math gives you the right answer, repeatedly, to 12 decimal places. And here is the contradiction that should make you stop and stare at the ceiling for a minute. The math behind these calculations, the mathematical foundation of perturbation theory and quantum field theory, is, by the standards of pure mathematicians, broken. The series that gives these miraculous predictions is what mathematicians call asymptotic. It does not converge. If you tried to calculate every term all the way to infinity, the series would blow up. It would diverge. It would give you nonsense. The reason the calculations work is because we stop at the right point before the series turns ugly. We extract 12 decimal places of agreement from a mathematical structure that, taken on its own terms, should not produce any sensible answer at all. Perfect predictions from flawed formalism. That is not a problem you find in any other branch of physics. So how did we get here? How did a theory built on math that does not technically work become the most precise scientific framework ever constructed? To answer that, we have to leave the experimental floor entirely and walk down into the basement, into the foundations of the theory itself, and that is where things start to get genuinely uncomfortable. Part 5. The universe is not made of particles. To understand why quantum field theory is so strange and so successful at the same time, you have to abandon the picture you probably have in your head about what the universe is made of. Most people, when they imagine the building blocks of reality, picture little balls, atoms as tiny solar systems, electrons as marbles orbiting a nucleus made of even smaller marbles, quarks as the smallest marbles of all. It is a comforting picture. It is also wrong. According to quantum field theory, the universe is not made of particles. It is made of fields. A field, in this technical sense, is a kind of structure that exists everywhere in space, all at once, with a value at every single point. The electromagnetic field is the easiest one to picture, because we already think of magnetic and electric forces as filling space. But quantum field theory says there is also an electron field. It exists everywhere. At every point in the universe, the electron field has some value. There is a quark field for each type of quark. There is a Higgs field. There are 17 fundamental fields in the Standard Model, all of them spread across the entire universe, all of them present at every location, all of them quietly humming with quantum activity. What we call a particle is just a localized excitation in one of these fields. An electron is not a tiny ball moving through empty space. An electron is a wave like ripple in the electron field, a packet of energy with specific properties that we register as a particle when we measure it. When you fire an electron through space, you are not really moving an object. You are propagating a disturbance through a field, the way a wave moves across the surface of an ocean, without the water itself travelling with it. And here is the consequence that I think is genuinely beautiful, and also genuinely strange. Every electron in the universe is identical, not similar, not just very alike, identical in every measurable way. They all have exactly the same mass, exactly the same charge, exactly the same magnetic moment. The reason is that there is only one electron field. Every electron we have ever seen, every electron that has ever existed, is the same kind of ripple in the same underlying structure. They are not copies. They are instances of a single thing. Now think about what this means for empty space. If fields are everywhere, and fields fluctuate quantum mechanically, then empty space cannot actually be empty. The uncertainty principle, which forbids any quantum field from sitting perfectly still, ensures that even in a region of space with no particles, the fields themselves are still humming with low-level activity. We call these quantum fluctuations. They produce what physicists sometimes call virtual particles, which is a slightly misleading name because these are not little particles that briefly exist. They are mathematical effects that show up in calculations, representing the way fields jiggle when nothing is supposedly there. The vacuum in quantum field theory is not nothing. It is a complex structured medium, full of activity, full of latent possibility. Every cubic centimetre of empty space is, according to the theory, a roiling sea of field activity. And this is not philosophy. We have measured it. The Casimir effect we mentioned earlier is a direct consequence of the vacuum being non-empty. The Lamb shift is a consequence. The anomalous magnetic moment of the electron is a consequence. The vacuum being active is one of the most experimentally confirmed predictions of quantum field theory. So here is where the central question of this whole video starts to come into focus. If reality at the deepest level we can currently see is already this strange, already this layered, with everything we call a particle being just a ripple in a field, with empty space being not empty, with 17 overlapping continuous structures filling the universe, then maybe quantum field theory itself is already telling us that reality has structure underneath. Maybe the field picture is the first hint that there are more layers further down, and maybe the reason the math behind the theory is so bizarre is that we are dealing with an effective description, a useful fiction, a precisely tuned interface to something we have not seen yet. To understand why the math is so bizarre, we have to talk about the most controversial fix in the history of physics. The thing the theory's own creators called a shell game. Part 6. Renormalization, the illegal fix. When physicists in the late 1940s first tried to use quantum field theory to calculate things like the electron's interaction with the vacuum, they ran into a wall. The wall was infinity. The calculations produced infinities everywhere. You would set up an integral that was supposed to give you the correction to the electron's mass from its interaction with the electromagnetic field, and the integral would diverge. It would not give you a number. It would give you the symbol for infinity, or worse, an expression that did not even make sense as a mathematical object. The same thing happened for the electron's charge. The same thing happened for the photon's properties. Every time you tried to include the effects of the electron interacting with itself, with its own electromagnetic field, the calculations exploded. For a few years in the 1940s, this was a genuine crisis. There was a real fear that quantum field theory was simply broken, that the framework could not be salvaged. Some of the brightest minds in physics, people like Wolfgang Pauli and Werner Heisenberg, considered the possibility that the whole approach needed to be abandoned. Then a procedure emerged. It was developed independently by several physicists, including Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, who would share the 1965 Nobel Prize for their work. The procedure was called renormalization, and here is what it did. The infinities, it turned out, could be sorted into specific categories. You had infinities in the electron's mass calculation. You had infinities in its charge calculation. You had infinities in a few other specific quantities. The renormalization trick was to notice that when you calculate something measurable, like the energy levels of hydrogen, the infinities from different parts of the calculation actually cancel each other out. You absorb the infinities into the so-called bare parameters of the theory, the underlying mass and charge of the electron before any quantum effects, and then you express your final answers in terms of the measured mass and charge instead. The infinities never appear in the final answer because they have been swept into definitions that you replace with experimental values. It works ridiculously well. The renormalized predictions of quantum electrodynamics are exactly the calculations that produced the 12 decimal place agreement we just talked about. But here is the thing. Even the people who developed renormalization were uneasy with it. Feynman himself was painfully honest about this. In his book QED, written for general readers, he flat out called the procedure a shell game. He said the way we deal with the infinities is hocus pocus. He said that even though the procedure gives the right answers, he could not bring himself to believe it was real mathematics. That is one of the people who invented the technique, who won the Nobel Prize for it, openly admitting that he was not sure the math was legitimate. Paul Dirac, who had been one of the founders of quantum mechanics and had built much of the mathematical structure that quantum field theory inherited, refused to accept renormalization at all. He called it ugly. He said any theory that required you to subtract infinities from infinities to get a finite answer was simply not a complete theory. He spent the latter part of his life looking for a better foundation, and he died without finding one. And yet, the procedure worked. Every prediction it made was confirmed. Every experiment that tested it returned a yes. The discomfort never went away, but the success kept compounding. So here we are, decades later, using a technique whose original architects called it a shell game, and getting the most precise predictions in the history of science out of it. The conceptual interpretation eventually became something like this. The bare parameters of the theory, the values that produce infinities, are not actually meaningful on their own. Only the measured parameters, the ones we can actually observe, are real. The infinities are an artifact of trying to push the theory beyond the energy scales where it is actually valid. When we subtract them away, we're essentially admitting that we're doing something a bit like averaging over an unknown high-energy region of physics, replacing it with a finite, measurable answer that captures the low-energy behavior we care about. That interpretation, which I'm about to develop in more detail, is what we now call effective field theory thinking. It rescues renormalization from being a shell game and reframes it as a feature of how layered descriptions of reality should work. But before we get there, we have to look at one more piece of the broken foundation. Because renormalization is not the only place where the math of quantum field theory goes wrong. The whole perturbative framework, the very engine that produces the 12 decimal place predictions, has a problem at its core that almost nobody talks about outside of specialized seminars. Part 7. The mathematics that should not exist. If you read carefully through the foundations of quantum field theory, you will find a result called Haag's theorem. It was proven in 1955 by a mathematical physicist named Rudolf Haag. And the conclusion of Haag's theorem is genuinely shocking, especially when you understand what it says. The theorem states, roughly, that the standard formulation of interactions in quantum field theory, the so-called interaction picture that almost every textbook uses to set up perturbation theory, is mathematically inconsistent. The picture assumes that you can treat a free, non-interacting field at one moment in time, then turn on interactions, then evolve the system, and recover a sensible interacting field at a later time. Haag proved that under the standard assumptions of relativistic quantum field theory, this construction does not exist. The free field and the interacting field are not in the same Hilbert space. They live in different mathematical universes that cannot be connected by a unitary transformation. In other words, the basic mathematical move that physicists make every single day in every quantum field theory calculation is technically illegal. The physicists know this, of course, but they also know that the calculations produce the right answers, so they keep doing it with a kind of pragmatic shrug and let the mathematicians worry about the foundations. There is more. The famous physicist Freeman Dyson, who did some of the earliest work on showing that quantum electrodynamics could be made to give consistent answers, also proved another uncomfortable result. He showed that the perturbation series in quantum field theory, the infinite sum over loop corrections that produces the 12 decimal place predictions, is not a convergent series, it is asymptotic. What that means in practice is this. The first few terms of the series get smaller and smaller, exactly as you would hope. The corrections diminish. The series appears to be converging toward a finite answer. But if you keep going, eventually, the terms start to grow again. And if you went all the way to infinity, summing every term, the series would diverge. It would give you infinity or worse gibberish. The reason the calculations work is that you stop at the right term. There is an optimal truncation point, somewhere around the term where the next correction would be roughly the same size as the experimental uncertainty. If you stop there, the answer is incredibly accurate. If you go further, the answer gets worse. And there is a deep reason for this. Dyson actually argued in a famous 1952 paper that the perturbation series in quantum electrodynamics has to be divergent because of a physical instability. If you imagine a world with the opposite sign of the fine structure constant, where electromagnetism would be attractive between like charges instead of repulsive, the vacuum itself would be unstable. It would explode into pairs of charged particles that would attract each other and drive the energy of the system to negative infinity. Such a world cannot be analytic in the coupling constant, which means the series expansion around zero coupling cannot converge. So the divergence of the perturbation series is not a calculational accident. It is built into the physical structure of the theory. We are dealing with a method that is, in the words of one mathematical physicist, wrong in principle but right in practice. We use it because nothing else gives us the kind of precision we need. We trust it because the predictions match experiment, but we cannot rigorously justify it. There is no complete, mathematically clean, non-perturbative formulation of the full standard model that we can fall back on when the perturbative one breaks. The math we use to describe the universe at its most fundamental level is, by the standards of pure mathematics, an unfinished construction site. And the deepest of these unfinished pieces is so notorious that there is literally $1 million bounty on its head. Part 8. The $1 million unanswered question. In the year 2000, the Clay Mathematics Institute, a private organization based in the United States, announced what it called the Millennium Prize Problems. These were 7 open mathematical questions, considered some of the most important and difficult unsolved problems in mathematics. Each one came with a reward of $1 million for whoever could provide a rigorous accepted solution. One of those problems, the Yang-Mills existence and mass gap problem, sits at the heart of the standard model. Yang-Mills theory is the mathematical structure that underlies the strong nuclear force, the force that binds quarks together inside protons and neutrons and holds atomic nuclei together. The standard model uses Yang-Mills theory as its skeleton. The Clay Institute's challenge is to prove rigorously that a quantum Yang-Mills theory exists in 4-dimensional spacetime, and that its mass spectrum has a positive lowest excitation, called the mass gap. 26 years later, the prize has not been awarded. The problem remains open. Now, this might sound like an obscure mathematical curiosity. It is not. What it means is that the mathematical foundation of the strong force, one of the 4 fundamental forces of nature, has not been rigorously proven to exist. We use the theory every day. We make predictions with it. We confirm those predictions in experiments. But strictly speaking, mathematicians have not yet shown that the theory is even mathematically consistent. The connection back to our central thread should be obvious. Quantum field theory, the most successful framework in the history of physics, is built on a foundation that includes a piece nobody has proven to be sound. And that piece is not optional. It is the part that describes how the universe holds itself together at the level of nuclei. So when we talk about the standard model being broken at its foundations, this is not a vague philosophical complaint. There is a literal $1 million problem sitting unsolved for over 2 decades that captures exactly how broken it is. So if the math is this shaky, why does the universe keep insisting the theory is right? And what happens when we apply that theory to the simplest and emptiest thing imaginable, the vacuum itself? Part 9. The vacuum that breaks the universe. We have been circling around the vacuum for a while now. Let me bring it fully into focus, because what quantum field theory predicts about empty space is not just strange. It is the largest known disagreement between theory and observation in the entire history of science. And the fact that physics still functions despite this disagreement is one of the deepest mysteries in modern thought. Here is the calculation. Every quantum field has 0-point energy. That is the energy it has even in its lowest possible state, due to the uncertainty principle forbidding it from sitting perfectly still. If you sum up the 0-point energy contributions of all the quantum fields filling the universe, the electron field, the photon field, the quark fields, and so on, you get a value for the energy density of the vacuum. That energy density, according to a straightforward application of quantum field theory, is enormous. The naive calculation, where you just integrate over all possible field modes up to the highest energy scale we think physics is meaningful, gives you a vacuum energy density of about 10 to the 113th joules per cubic meter. You can argue about the cutoff and shave that down, but even with very generous assumptions, the predicted vacuum energy is huge. Now compare that to what we actually measure. We do measure the vacuum energy. We call it the cosmological constant, and it is responsible for the observed accelerating expansion of the universe. The accelerating expansion was discovered in 1998, confirmed by multiple independent observations since then, and it implies that empty space has a specific, very small, positive energy density of about 10 to the negative 9th joules per cubic meter. The difference between the predicted value and the observed value is roughly a factor of 10 followed by 122 zeros. 122 zeros. To give that a sense of scale, the number of atoms in the observable universe is around 10 to the 80th. So the disagreement between what quantum field theory predicts for the vacuum energy and what we actually observe is roughly 10 to the 42nd times larger than the total number of atoms in the universe. That is the worst prediction in the history of science. It is so bad that physicists have a name for it. They call it the vacuum catastrophe, or sometimes more politely the cosmological constant problem. And here is why it is more than just an embarrassment. If quantum field theory's prediction were correct, the universe could not exist in anything like its current form. The vacuum energy would be so high that space would expand at an unimaginable rate. Galaxies could never form, stars could never coalesce, atoms could not even hold together long enough to call themselves atoms. The universe would have torn itself apart in the first instant, and there would be no us, no you, no me, no anything. Yet here we are. The universe is full of structure. Galaxies exist, stars burn, atoms are stable. The cosmological constant is small enough that the universe got plenty of time to build up the gravitational structures we see, and only recently, in the last few billion years, has the dark energy started to dominate and accelerate the expansion. So either quantum field theory is incomplete, or there is some mysterious mechanism that almost perfectly cancels the predicted vacuum energy down to the tiny value we observe, or both. Most physicists suspect it is some combination. There is presumably a deeper layer of physics that produces an enormous cancellation, leaving behind only the small residual we measure. But nobody knows what that mechanism is. Nobody knows where it comes from. Nobody can derive the observed cosmological constant from first principles, which means quantum field theory is in the bizarre position of being extremely accurate in some places, like the electron's magnetic moment, and catastrophically wrong in others, like the vacuum energy. That is not how a fundamental theory of nature is supposed to behave. A fundamental theory should either be right everywhere, or it should fail in clean, identifiable ways. Quantum field theory does neither. It succeeds wildly in domains we can probe with precision experiments, and fails wildly in places where the consequences would be cosmic scale. And that is the strongest hint we have that the theory is not fundamental at all. It is a layer. It captures something about how physics behaves in certain regimes, while being almost entirely silent on what is happening underneath. The success and the failure are not contradictory. They are exactly what you would expect from an effective description that is calibrated to certain scales and incomplete at others. So if the universe is so finely tuned that we exist despite a theory, predicting we should not, what is doing the tuning? And why is reality so suspiciously stable when the math says it should not be? Part 10. Why nothing should exist but does. The vacuum catastrophe is not just a numerical embarrassment. It is the most striking example of a pattern that runs through all of fundamental physics, the pattern of fine-tuning. When we look at the values of the constants in the Standard Model, the masses of the particles, the strengths of the forces, the energy of the vacuum, we find that they sit at very specific values that allow for the universe we see. Shift the proton's mass by a fraction of a percent, and atoms become unstable. Shift the strength of the strong force a little, and stars cannot fuse hydrogen into helium. Adjust the cosmological constant by even a tiny amount and the universe collapses or disperses too quickly to form anything. The cancellation that gives us the small observed cosmological constant requires that the various contributions from quantum field theory, contributions that individually are enormous, cancel each other to about 1 part in 10 to the 122nd. That is the most precise cancellation in physics. It is more precise than any experimental measurement. It is more precise than any theoretical calculation, and nobody knows why it happens. Quantum field theory does not predict the cancellation. It does not even hint at why such a cancellation would occur. The theory simply gives you a huge number, and the universe quietly hands back a tiny one, and physics has to swallow the discrepancy without choking. There must be something missing. There must be a mechanism, a symmetry, a structure, something that explains why the vacuum energy is what it is, and whatever that something is, it is not part of quantum field theory as we currently understand it. It is part of a deeper layer. So we have a theory that is precise to 12 decimal places in some calculations, and wrong by 122 orders of magnitude in others. We have a vacuum that should be cataclysmic, but is instead barely energetic. We have a universe that should not exist by the lights of its most successful description, but exists anyway. That is not a clean story. That is a story about a theory standing on top of something it cannot see, gathering its precision from the surface while a deeper mystery quietly carries the whole edifice. And in the 1970s, a physicist named Kenneth Wilson came along and gave physics a new way to think about exactly this kind of situation. He gave us the language we needed to talk about quantum field theory, not as the bottom of physics, but as a layer in a tower. Part 11. The idea that changes everything. Kenneth Wilson did not initially set out to overhaul our understanding of fundamental physics. He was working on a more concrete problem, the problem of phase transitions, things like the way a magnet loses its magnetism when you heat it past a certain temperature, or the way water and steam can become indistinguishable at the critical point. These problems involved physics happening at many different length scales at once, and the standard tools were failing. Wilson developed a technique called the renormalization group, which let him systematically track how a physical theory changes as you zoom in or zoom out, as you look at the system at different scales of distance or energy. What Wilson realized, and what eventually transformed quantum field theory itself, was that physics is naturally organized by scale. The behavior of a system at one scale is determined by certain effective laws, and those laws can be very different from the laws at another scale, even though they are ultimately describing the same underlying reality. When you zoom in, you see new degrees of freedom, new physics, new structure. When you zoom out, things average out and the apparent laws become simpler, more universal, less dependent on the microscopic details. For phase transitions, this insight let Wilson explain why systems with totally different microscopic descriptions, like a magnet and a fluid near its critical point, often behave in remarkably similar ways. The microscopic details are washed out at large scales, and what remains is a universal effective description. He won the Nobel Prize for this in 1982. But the idea had vastly bigger implications. Once you start thinking about quantum field theory through Wilson's lens, the whole structure of the theory looks different. The infinities that plagued the early calculations, the ones that required renormalization to tame, suddenly stop looking like a defect. They start looking like a feature. They are the way the theory is telling you that you have pushed it beyond the scale where it is valid. The infinities represent your ignorance of the physics happening at higher energies, at smaller distances, that you have not included in your description. Renormalization is no longer a shell game. It is a procedure for separating what matters at the scale you care about from what is happening at scales you have not resolved. The bare parameters that produce infinities are not the real, fundamental parameters of physics. They are the parameters of the unknown deeper theory, expressed in a language that is only useful when you let some of them be infinite to absorb your ignorance. The measured parameters, the ones that show up in experiments, are the effective parameters that describe physics at the scales you can actually probe. This perspective is called effective field theory, and once you accept it, quantum field theory itself takes on a completely different status. It is no longer a candidate for the final fundamental theory of physics. It is, by construction, a low-energy approximation. It is the description that is valid at the scales where we have done experiments. At higher energies, at smaller distances, the description must break down and be replaced by something deeper. Newtonian mechanics is a low-energy, low-velocity approximation of relativity. Classical electromagnetism is a classical limit of quantum electrodynamics. Quantum electrodynamics itself is part of an effective theory that should give way to whatever physics rules the very highest energies, scales we have never experimentally accessed. Each layer is valid in its own domain. Each layer fails when you push it too far, and there is no fundamental reason to expect that any particular layer is the bottom. The renormalization mystery dissolves. The infinities become natural. The success of the theory at low energies is exactly what you would expect from a well-constructed effective theory. The failures at extreme scales, like the cosmological constant problem, are exactly the symptoms you would expect from missing physics at the deeper layer. Quantum field theory is not a flawed fundamental theory. It is a successful effective layer, and it points down into something we have not yet seen. Part 12. The Tower of Descriptions. Once you start thinking in terms of effective field theory, the whole architecture of physics starts to look like a tower. At the top you have the everyday phenomena of human-scale physics, solid objects, fluids, gases, the macroscopic world of cars and weather and biology. These are described by classical mechanics, classical electromagnetism, classical thermodynamics. That is layer 1. Zoom in a level and the classical descriptions start to fail. You enter the regime of atoms and molecules, where quantum mechanics takes over. The classical orbits of electrons around nuclei are replaced by probability clouds. The continuous flow of energy is replaced by discrete quanta. That is layer 2. Zoom in further, and quantum mechanics in turn becomes inadequate. At very small distances and very high energies, the relativistic quantum behavior of fields becomes important, and you need quantum field theory. This is the layer we have been talking about for the entire video. That is layer 3. Now look upward instead. At larger scales, the underlying quantum mechanics gets averaged away and effective laws emerge. The entire field of thermodynamics, with its laws about entropy, heat and temperature, is an emergent effective description that arises from the underlying microscopic dynamics of countless molecules. You do not need to know the quantum state of every air molecule in this room to predict whether the room will heat up or cool down. You just need temperature, pressure, and a few other macroscopic variables. The microscopic details have been absorbed into an effective description that captures everything that matters at the larger scale. The same pattern repeats throughout science. Chemistry is, in some sense, an effective theory of the underlying quantum mechanics of electrons and nuclei. Biology is an effective theory of the underlying chemistry. Each layer has its own laws, its own concepts, its own valid range of application. Each layer is connected to the layer below by some kind of approximation or averaging procedure, but each layer can be developed and used without fully understanding the layer underneath. This is one of the deepest patterns in nature. Reality, at least as we describe it, is layered, and every layer is real, in the sense that the laws governing that layer accurately describe the phenomena at that scale. But every layer is also incomplete, in the sense that to understand why the laws have the form they do, you have to descend to a deeper layer. Now here is the question that keeps physicists awake at night. Does the tower have a bottom? Is there some fundamental layer at the very bottom that is not itself effective, that is not built on top of anything else? Or does the tower go down forever, with each layer being effective relative to a deeper one, in an infinite regress? Quantum field theory cannot answer this question. It cannot even ask it from the inside. From within the framework, all you can see is the layer you're in and the suggestion that there is something below. The deeper structure, if it exists, is not visible from the surface. We have no experimental access to scales much beyond what current colliders can probe. We have no theoretical framework that lets us calculate from a deeper theory and derive quantum field theory as its low-energy approximation, except in highly speculative scenarios that have not been experimentally tested. So we are stuck on a layer, looking down into darkness, trying to figure out what is there from the texture of our own description. And what we see in that texture, the cancellations, the fine-tunings, the asymptotic series, the renormalization procedures, all of it points toward a richer structure underneath. Physics has become, in a sense, a kind of compression scheme for reality. Each layer compresses the complexity of the layer below into a manageable set of effective laws. The compression is leaky, which is why the deeper structure peeks through in places like the cosmological constant. But the compression is also extremely efficient, which is why the surface descriptions can be so precise. The question we have to ask now is, what kinds of theories could be at the next layer down? What does the universe look like underneath quantum fields? Part 13. What could be underneath QFT? If quantum field theory is an effective description, then the natural question is, an effective description of what? What kind of structure could exist at scale smaller than anything we have ever directly probed, that produces quantum field theory as its low-energy approximation? Several candidate frameworks have been developed over the past several decades. None of them have been experimentally confirmed. All of them are deeply mathematical, deeply speculative, and deeply controversial within the physics community. But they share a common goal, which is to find what is underneath. The most famous candidate is string theory. The basic idea of string theory is that what we call particles are not point-like field excitations, but tiny vibrating strings of energy. Different vibrational modes of the string correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. The mathematical structure that emerges from this picture is so rich that it automatically includes a quantum theory of gravity, which has been the holy grail of theoretical physics for nearly a century. String theory is mathematically consistent in ways that quantum field theory is not. It does not have the same kinds of infinities, because the extended nature of the string smooths out the singularities that plague point particles. But string theory comes with prices. It requires extra dimensions of space, 6 or 7 of them depending on the version, beyond the 3 we observe. Those extra dimensions have to be curled up in tiny configurations to hide them from our view. String theory has produced a vast landscape of possible solutions, possibly 10 to the 500th distinct vacuum states, with no clear way to identify which one corresponds to our universe. And the energy scale at which string effects would become directly visible is so high, far beyond any conceivable particle accelerator, that direct experimental tests seem impossible. String theory is beautiful, mathematically sophisticated, and untested. A different candidate is loop quantum gravity. Where string theory tries to find a quantum description of gravity by extending particles into strings, loop quantum gravity tries to quantize space-time itself. In this picture, space is not a smooth, continuous manifold. It is a network of discrete loops or knots, with area and volume coming in tiny indivisible units, like the way energy comes in quanta. Loop quantum gravity makes specific predictions about what happens in extreme gravitational situations, like inside black holes or at the moment of the Big Bang. It does not predict extra dimensions. It does not produce a unified picture of all forces, but it does produce a clean quantum theory of gravity. It is also, like string theory, very far from experimental verification. Then there are causal sets, where the fundamental entities are not particles or fields or strings, but discrete events, with a partial ordering describing which events can causally influence which others. Space-time emerges from the network of causal relations. This approach takes the deep idea that causality should be fundamental and makes it the building block of everything else. The holographic principle is another major idea. It suggests that the information content of a region of space can be encoded on its boundary, like a 3-dimensional hologram emerging from a 2-dimensional surface. This idea, partly inspired by the entropy of black holes, suggests that what we think of as 3-dimensional reality might actually be a projection of information stored on a lower dimensional surface. The most concrete realization of this is the ADS-CFT correspondence, which links certain quantum field theories on a boundary to gravitational theories in a higher dimensional bulk. There is also asymptotic safety, an approach that tries to make sense of quantum gravity within the framework of quantum field theory itself by finding ultraviolet fixed points where the theory remains well behaved at arbitrarily high energies. Each of these frameworks tries, in its own way, to resolve the issues that plague quantum field theory. Each of them tries to handle the infinities, to unify the forces, to explain why the constants of nature have the values they do, to provide a deeper layer that produces quantum field theory as a low-energy approximation. None of them have succeeded at the level of producing testable predictions that have been confirmed by experiment. The physics community is split into camps. Some bet on strings, some bet on loops, some bet on holography. Some bet that none of these are right and we have not yet discovered the correct framework. The honest truth is that we do not know what is underneath quantum field theory. We have hints, we have constraints, we have mathematical guesses, but the experimental data have not been able to push us decisively in any direction, which leads some thinkers, especially philosophers and a few outlier physicists, to entertain hypotheses that go even further afield. Part 14. The Simulation and Emergence Hypothesis. There is a class of ideas about the deeper layer of reality that most physicists treat carefully because they sit on the edge of testability. The most famous is the simulation hypothesis. This is the philosophical proposal that what we experience as physical reality might be the output of some kind of computational process running in a substrate we have no access to. The argument typically goes that if any sufficiently advanced civilization ever produces simulated worlds with conscious inhabitants, the simulated inhabitants will eventually outnumber the base-level inhabitants by a huge margin, and so any randomly chosen mind, including yours and mine, is more likely to be in a simulation than at the base level. As a serious scientific claim, it is essentially impossible to test, because any simulation good enough to produce observers like us would presumably look indistinguishable from a non-simulated reality. Most physicists do not engage with the simulation hypothesis as physics. They engage with it, when they engage with it at all, as philosophy. But the underlying intuition that what we call physical reality might be the surface output of an underlying computational or generative process is not as fringe as it sounds. It overlaps significantly with serious ideas about emergence in physics. There are perfectly mainstream proposals that space-time itself, with its 3 dimensions and 1 dimension of time and its smooth metric, might emerge from a deeper substrate of quantum information or causal relations. There are proposals that the laws of physics might not be eternally fixed, but might themselves emerge from some kind of selection process in a multiverse of possible laws. The boundary between rigorous emergence and speculative simulation is real, but not always clean. What unites all these ideas is the intuition that quantum field theory feels computed. It feels like the output of something rather than the bottom of everything. The mathematical structures it presents, the symmetries, the cancellations, the fine-tunings, all hint at a generative process behind them. Whether that process is literal computation in some hidden substrate, or an emergent pattern from a deeper physical theory, or something we do not yet have a vocabulary for, the intuition is the same. There is something underneath. Most physicists prefer to keep their feet planted in proposals that are at least in principle testable. But the broader cultural conversation about what reality might really be, including the simulation idea, captures a feeling that physicists themselves often share even if they do not say it publicly. The feeling that the surface we're looking at is too neat, too computed, too algorithmic to be the deepest layer. Part 15. Why Physics Feels Complete and Incomplete. At the same time, we have arrived at a strange place. On one hand, modern physics feels almost finished. The Standard Model, despite all the issues we have discussed, accurately describes every particle physics experiment ever conducted. General relativity accurately describes every gravitational phenomenon we have observed. Together, these two theories cover essentially every empirical fact about the physical universe at the scales we can directly probe. There are no observed phenomena that flatly contradict either theory in its proper domain of application. From this perspective, physics looks complete. We have the laws. The laws work. They predict experiments to extraordinary precision. What more do we want? On the other hand, physics has never felt more incomplete. The Standard Model has dozens of free parameters whose values are not predicted by the theory and have to be measured and inserted by hand. The cosmological constant problem remains as bad as ever. Dark matter and dark energy, which together make up about 95% of the universe's energy budget, are not described by the Standard Model. Quantum gravity remains unresolved. The mathematical foundations of the framework are still on shaky ground, with Yang-Mill's existence still open and renormalization still requiring conceptual interpretation. From this perspective, physics looks like a half-finished house. The walls are painted beautifully, but the foundation is cracked and the roof has holes. This contradiction is not new. Physics has felt both nearly complete and dramatically incomplete for decades. What is changing is the way physicists talk about it. Increasingly, physicists are willing to say openly that the Standard Model is not meant to be a final theory. It is an effective theory, valid up to some energy scale beyond which new physics must take over. The question is not whether quantum field theory will eventually be replaced. It will. The question is what will replace it, and at what scale, and how we will find out. The reason quantum field theory keeps producing precise predictions despite its broken foundations is, in a sense, the same reason a well-calibrated map of a coastline can be useful even if you do not know what the underwater geology looks like. The map captures regularities at the level you care about. The deeper structure is invisible to the map but does not need to be visible for the map to work. Symmetry constraints play a huge role here. Quantum field theory inherits powerful symmetries, like Lorentz invariance from relativity, gauge invariance from the structure of the forces, and various internal symmetries connected to the conservation of charge, momentum, and other quantities. These symmetries are extremely rigid. Once you commit to a theory that respects them, the form of the equations becomes highly constrained. There are not many ways to write down a relativistic gauge invariant locally interacting quantum field theory. The constraints are so strong that the predictions are largely determined by the symmetries themselves, almost regardless of the deeper microscopic details. This is why effective field theory works. The deeper details get washed out and only the symmetry-constrained, symmetry-compatible, low-energy behavior survives. So physicists often joke, half seriously, that quantum field theory keeps giving the right answers for the wrong reasons. The mathematical apparatus is dubious. The renormalization is hand-wavy. The series is divergent. But the symmetry constraints are so strict that any theory respecting them at low energies must produce essentially the same predictions, no matter what the deeper physics looks like. The right answers are forced by symmetry, even if the mathematical bookkeeping looks suspicious. That insight is part of why physicists trust the predictions even while distrusting the foundations. And it leads us into the final stretch of our journey, where we ask what all of this means for our picture of reality itself. Part 16. The real discovery is not a particle. Let me come back to the title of this video for a moment, because I owe you a moment of honesty about what we have actually been discussing for the last several thousand words. Scientists just discovered another layer of reality hiding inside quantum fields. That is the headline. That is what got you here. And you have probably been waiting, somewhere in the back of your mind, for me to announce some specific new particle, some specific experimental result, some specific moment when reality cracked open and a new piece visibly fell out onto the laboratory floor for everyone to inspect. Some press conference at CERN with people pointing at a screen and a graph showing a peak that should not be there. Some new fundamental constituent of nature with a strange name and a strange property, and a clean experimental signature that confirms a previously theoretical prediction. That is the way these stories usually go in physics journalism. the Higgs in 2012, gravitational waves in 2015, the first image of a black hole in 2019. A specific moment, a specific image, a specific announcement, that is not what happened here. Let me say that as plainly as I can, because the rest of what I want to tell you depends on it. There is no new particle, there is no new force, there is no new dimension that has been directly observed in any laboratory anywhere in the world. Nothing has crossed the threshold from theoretical speculation to confirmed experimental reality. If you came to this video expecting a specific announcement of a specific finding, the kind of thing that fits in a tweet, I have not been able to deliver that, and I want to be straight with you about why. Because the discovery I am actually trying to communicate is stranger than that, and it is harder to package, and it does not come with a clean photograph or a single moment of triumph. But it is, I think, more profound than any single particle discovery would have been. It is the kind of thing that changes how you look at every particle discovery that has ever been made. What happened, and what is continuing to happen, across physics labs and seminar rooms and theoretical physics journals around the world, is something subtler and in some ways more profound than a new object falling out of an experiment. Physicists have been slowly accumulating a structural insight about the theory itself, not about a thing the theory describes, about the theory, about what kind of object quantum field theory actually is, and what its successes and failures are telling us about the deeper architecture of reality. The insight has been building for decades, accumulating one piece at a time, often in technical papers that never make it into popular science coverage because they are not about a discovery in the traditional sense. They are about reinterpretation, about reframing, about reading the same data and the same equations differently than we used to read them. The pattern of every anomaly resolving in favour of the standard model is part of the insight. Each time an experimental discrepancy shows up, generates excitement, and then quietly closes through better measurements or better calculations, that is not just a failed search for new physics. That is data. That is the universe telling us something about how stable the theory really is. The pattern of renormalization being recast over time, not as a calculational trick that physicists hold their nose to use, but as a natural feature of how layered descriptions of reality work, is part of the insight. The pattern of asymptotic series being understood as a generic property of effective theories, rather than a flaw in this particular one. The pattern of fine-tuned cancellations like the cosmological constant being recognized as signals of a deeper structure, rather than indictments of the surface description. The pattern of effective field theory thinking gradually replacing the older dream of a fundamental field theory at the deepest level of physics. All of these threads point to the same conclusion. They have been pointing at it for years. Most physicists working in foundations are now willing to say it openly, even if it has not fully filtered into popular discourse yet. Quantum field theory is not just a theory. It is a layer. It is a description that sits on top of a deeper structure that we have not yet directly observed, but whose existence is increasingly clear from the texture of the layer above it. The discovery is not a new object you can hold or photograph or detect. The discovery is about the nature of the layer itself. It is the realization that we have been looking at a surface all along, and the surface has been telling us, in its own elegant mathematical language, in the very pattern of its successes and its failures, that there is something underneath. We have been listening to the language of physics so closely for so long that we are finally starting to hear what it has been saying about itself. And what it has been saying is that it is not the whole story. It is a chapter. It is a beautifully written, exquisitely precise chapter in a much longer book. Here is the part that I think is genuinely counterintuitive, and I want to make sure I land it clearly. The fact that quantum field theory keeps holding up under experimental tests, that no anomaly survives long enough to break it, that every precision measurement matches its predictions to absurd accuracy, this is not evidence that quantum field theory is the bottom of physics. Most people, hearing about a theory that just keeps being right, would conclude that the theory must be fundamental. That is the natural intuition. If a theory is right, it must be the truth. But the layered interpretation says the opposite, and once you see why, it is hard to unsee. The empirical success of quantum field theory is evidence that the layer is well separated from the deeper physics, that the scale gap between the energies we can probe and the energies where the deeper structure becomes visible is large enough that the deeper layer does not directly intrude on the experiments we can currently perform. The theory is not stable because it is true at the deepest level, it is stable because the deeper level is far away. Think about what would happen if the deeper physics were close in scale to what we can probe. We would expect to see deviations. Anomalies would not just close, they would survive better measurements. New particles would show up. Unexplained patterns would persist year after year. The standard model would have visible cracks that would widen as we looked at them more carefully. Instead, what we see is a remarkable cleanness, a remarkable stability, an almost suspicious level of agreement between theory and experiment everywhere we look. That is exactly what an effective theory looks like when the underlying physics is far away in scale. The cleanness is the signature. The stability is the fingerprint of separation. We are not seeing the theory hold up because nothing is below it. We are seeing the theory hold up because whatever is below it is too far away to leave detectable traces in our current experiments. The real discovery, in other words, is epistemic. I want you to sit with that word because it captures what is actually new here. It is not a discovery about the world in the sense of finding a new object in the world. It is a discovery about our own descriptions of the world and what those descriptions are telling us about themselves, about the relationship between theory and reality, about the kind of knowledge our best physics actually constitutes, about how to read the silences and the cancellations and the suspicious successes alongside the spectacular accuracies. Physics, for most of its history, has been the science of discovering new objects, new planets in the night sky, new elements in the periodic table, new particles in the rubble of high-energy collisions, new cosmic structures at the edges of the observable universe, object after object, added to the inventory of things the universe contains. And those discoveries are still happening and still important. But increasingly, especially in fundamental physics, the field is becoming something else as well. It is becoming the science of discovering its own limits. The structure of the theory itself is becoming the source of insight. The way the framework constrains what we can predict, what we can calculate, what we can know in principle, all of this is emerging as data about reality in its own right. We are reading the constraints of our own framework, and we are learning, from the very shape of those constraints, that the framework is not the final story. There is another layer. We just cannot see it directly yet. And the way we know it is there, the way we are confident enough to claim it without ever having observed it, is by reading the contours of the layer we can see. The surface tells us about the depths. The map, by its own structure, reveals that there is more territory beyond its edges. That is the discovery. It is quieter than a new particle, but it might be more important than any single particle has ever been. Part 17. The layered reality interpretation. Let me try to put this all together in one clean picture, because I think it is genuinely worth pausing to appreciate what we have actually arrived at. Reality, as far as we can currently tell, is layered, not metaphorically, not poetically, structurally. The physics itself is telling us this, in the very form of the equations we use to describe it, and the picture, once you see it, is one of the most elegant frameworks anyone has ever proposed for what the universe actually is. At the surface, the layer we live in every single day, we have the macroscopic world, objects you can hold, motions you can see, forces that push and pull on bodies large enough to register in your senses, fluids that flow through pipes, gases that fill rooms, planets that orbit stars. This is the world of classical physics, of Newton and Maxwell and Einstein, the world of effective theories of large-scale matter. It is the layer where rocks are rocks and water is water, and the sun comes up tomorrow because of equations we figured out centuries ago. It works. It works beautifully. You can land a spacecraft on a comet using these laws. You can build a bridge that holds up a city. You can predict eclipses thousands of years in advance. This layer is real, and the laws governing it are accurate in their own domain of application. Now zoom in. Zoom in past the human scale, past the millimeter, past the micrometer, until you reach the world of atoms and molecules. The classical descriptions start to break down. The smooth, deterministic motion of a large object gives way to something stranger. Electrons do not orbit nuclei in tidy little circles. They occupy probability clouds. Energy does not flow continuously. It comes in discrete quanta. The certainties of classical physics dissolve into the probabilistic structure of quantum mechanics, and from quantum mechanics emerges all of chemistry, the entire periodic table, every chemical reaction, every molecule that makes up your body and the body of every living thing on this planet. That is layer 2, quantum mechanics, and the chemistry that emerges from it. A different layer with different rules, valid in its own range, breaking down when you push it too far in either direction. Zoom in further, past atoms, past nuclei, into the realm of fundamental particles and the forces that govern them. The quantum mechanics of the previous layer is no longer enough. You need relativity in there. You need fields. You need the full machinery of quantum field theory and the standard model. This is layer 3, and it is the layer we have spent this entire conversation on. Quarks and leptons, photons and gluons, the Higgs field giving mass to particles through symmetry breaking, the strong, weak and electromagnetic forces all unified under the same field theoretic framework. 12 decimal places of precision. The most accurate description of the universe humans have ever produced, and, as we have seen, also a description with cracks running through its foundations. And below that, we have something. I want you to sit with that word for a second. Something. Not nothing. Not a mystery in the lazy sense. Not a placeholder for ignorance. We know there is a layer below quantum field theory, because the structure of quantum field theory itself demands it. Something that produces quantum field theory as its low-energy effective approximation. Something that resolves the cosmological constant cancellation, that 122 order of magnitude near miracle that allows our universe to exist instead of tearing itself apart in the first instant. Something that includes gravity in a quantum mechanically consistent way, which is the holy grail nobody has reached. Something that explains the values of the constants of nature, the masses, the coupling strengths, the cosmological parameters that all sit at very specific, finely tuned values that allow stars to form and atoms to be stable and life to eventually emerge. Something that explains the structure of the symmetries that constrain the equations so tightly that the predictions come out right, almost regardless of what is happening underneath. Something that explains the fine-tunings, the cancellations, the suspicious cleanness of the universe at the scales where we live. We do not know what that something is. Let me say that plainly, because it is one of the most honest sentences in modern physics. We do not know. We have candidates. Strings vibrating in extra dimensions, producing the spectrum of particles we observe as different harmonics of a single underlying object. Loops of quantized space and time, where the fabric of reality itself comes in indivisible chunks. Causal sets, where the fundamental thing is not space or time but the network of cause and effect relationships between elementary events. Holography, where what we experience as three-dimensional reality is somehow encoded on a lower dimensional boundary, like an extraordinarily detailed cosmic projection. Asymptotic safety, where quantum field theory itself is rescued at the highest energies by mathematical fixed points we have not yet fully mapped. Each candidate is a guess, a sophisticated, mathematically beautiful, sometimes breathtakingly creative guess, an extrapolation from what we know toward what we do not, a mathematical structure that might fit. None of them are confirmed. None of them have produced the kind of decisive experimental evidence that would let us point and say, yes, this is the next layer down. But here is what I want you to notice. The layered picture itself does not depend on any specific candidate winning. It does not require strings to be right, or loops to be right, or holography to be right. It depends only on a single recognition. The recognition that quantum field theory, despite its successes, has the formal structure of an effective theory. And effective theories, by their very nature, sit on top of something deeper. That is the insight. That is what has shifted in the foundations of physics over the past several decades. Not a new particle, not a new force. A new understanding of what kind of thing our most successful theory actually is. That recognition is what is new. Or rather, it is what is becoming consensus. For most of the 20th century, physicists treated quantum field theory as a candidate for fundamental physics. The hope, the dream, was that with enough work, the right version of quantum field theory would turn out to be the bedrock of reality. A finite version where the infinities never appeared in the first place. A non-perturbative version where you did not have to truncate divergent series to get sensible answers. A fully consistent version where Haag's theorem and the rest of the foundational issues evaporated. Generations of brilliant minds chased that dream. They built mathematical structures, proposed new approaches, tried to clean up the inconsistencies, and the dream has been steadily eroded over the decades by the very issues we have walked through together in this video. The mathematical inconsistencies that nobody has resolved. The asymptotic series that diverges no matter how cleverly you arrange it. The cosmological constant problem that just refuses to go away. The unresolved Yang-Mills mass gap that still sits open at the Clay Mathematics Institute. The lack of any obvious path from quantum field theory to a consistent quantum theory of gravity. Slowly, almost reluctantly, the consensus has shifted. Quantum field theory is now widely understood by working physicists as an effective description, not a candidate for ultimate truth. And this shift, this quiet revolution in how physicists think about their own framework, is what gives the layered reality interpretation its real power. Because if quantum field theory is an effective layer, then there is no contradiction between its empirical success and its mathematical incompleteness. Of course it succeeds at the scales it was built for. That is what effective theories do. Of course it fails in places where the deeper physics is doing the heavy lifting, like the vacuum energy or the values of the fundamental constants. That is also what effective theories do. Of course its math looks suspicious in places where we are pushing it past its domain of validity. The whole picture becomes coherent, even elegant. The strangeness we have been wrestling with for 2,000 words and 20 parts dissolves into a clean structural insight about what physics has actually been doing all along. What remains is the question of what is at the next layer down, and whether beyond that there is yet another layer, and another, and another. Whether the tower has a bottom, with some final layer of physics that is not itself effective relative to anything deeper, or whether reality is layered all the way down, with each layer being effective relative to a deeper one, in an unending regress, is something physics cannot currently answer. It might be a question we cannot answer in principle. Because we are always inside some layer, looking down through the haze, never able to step outside the system to see whether it has a base. There is no view from nowhere. There is no place to stand outside reality and look at it as a whole. Every measurement, every theory, every flash of insight happens from within a layer, and that layer is the only territory we have direct access to. But the layered picture, as far as it goes, is the most honest summary we have of what the past several decades of physics have actually taught us. It is not a final answer. It is not a theory of everything. It is a recognition of what we are doing when we do physics, and what kind of relationship our best descriptions actually have to the reality they describe. We are mapping layers. The maps are extraordinary, and the territory underneath the maps is still, in large part, waiting to be seen. Part 18. What reality might mean if this is true. If the layered reality interpretation is correct, it does something subtle but profound to our concept of what reality fundamentally is. And I want to take a few minutes here to really sit with that, because the implications are bigger than they look at first glance. We are used to thinking of reality as made of stuff, objects, things, particles, fields, solid, definite, locatable items that exist independently of anything else. Pick up a rock, and the rock is made of molecules, and the molecules are made of atoms, and the atoms are made of subatomic particles, and the particles are excitations of fields. Each step down, in the traditional picture, brings you closer to the real building blocks. The fundamental layer in this view would be the layer of the most basic stuff, the smallest, simplest, most indivisible blocks of which everything else is constructed. Find the bottom layer, and you find the ultimate furniture of the universe. You find the things that exist for real, that are not made of anything else, that just are what they are. That is the dream that has driven a huge portion of human inquiry for thousands of years, from the ancient Greek atomists to the particle physicists building accelerators today. The layered picture suggests this might be the wrong metaphor entirely, and I do not say that lightly. Reality, in this new picture, is not so much a collection of objects as a process of approximation. That is a strange sentence to swallow on first reading, so let me say it again in a different way. The layers are not stacks of progressively smaller objects. The layers are progressively better descriptions of something whose ultimate nature may not be object-like at all. Each layer is a way of describing the layer below, valid in its own range, breaking down outside its range. Each layer has its own concepts, its own laws, its own ontology, its own language for talking about what exists. The macroscopic layer talks about rocks and rivers. The chemical layer talks about molecules and bonds. The quantum field layer talks about excitations and symmetries. And each of these vocabularies is real, in the sense that it accurately captures the patterns at its scale. But none of the layers, possibly, is the final one. There may be no bottom vocabulary that bottoms out in the real building blocks. There may just be more layers, more descriptions, more approximations, going down as far as we can probe and possibly farther. Reality, then, is less like a building made of bricks, and more like a series of nested maps, each more detailed than the last, with no guarantee that there is an actual territory at the bottom that is itself unmapped. Read that again, because it took me a long time to absorb it the first time I encountered the idea. We're used to maps and territories being separate things. The map describes the territory, and the territory exists independently of the map. But what if, in physics, the territory itself is just another map relative to a deeper one? What if every layer that looks like territory from above turns out to be a map when you zoom into it? You never reach the territory, you just keep finding more maps. And the question of whether there is some final territory underneath all the maps becomes a question physics may not be equipped to answer. If you take this seriously, several traditional questions about physics start to look different. They do not just get answered differently, they become different questions entirely. What is a particle, really? In the layered picture, a particle is not a fundamental object. It is a localized excitation of an effective field that itself emerges from a deeper structure, that itself probably emerges from something deeper still. The particle is a useful concept at one layer. It is the right way to think about reality at the scales where particle physics experiments operate, but it does not have to be the fundamental thing in the universe. The whole notion of fundamental thingness might just not apply once you go deep enough. The electron you think you have located in a detector is real at its layer, real in the sense that it produces predictable behaviors and measurable consequences. It just might not be a thing in the way you've been imagining things. What are the laws of physics, really? In the traditional view, the laws are eternal absolute truths inscribed somewhere outside reality, governing the behavior of stuff from above like cosmic legislation. The layered picture says no. The laws are not eternal. They are not absolute. They are effective rules that emerge at certain scales, constrained by symmetries and consistency conditions, valid within their domains, breaking down outside. The laws are real, in the sense that they accurately describe phenomena. They predict experiments, they organize our understanding, but they may not be the ultimate description of what is happening. They may be, themselves, surface features of something deeper, in the same way that the laws of thermodynamics are surface features of the underlying molecular dynamics. There is no thermodynamic law that exists independently of the molecules. The laws emerge from the collective behaviour, and the laws of quantum field theory may emerge in exactly the same way from whatever is underneath, with no ultimate cosmic legislation behind them, just patterns in the deeper structure that look like laws when you average over them at our scale. What is an observer, really? This one might be the strangest question of all. In the layered picture, an observer is always inside one of the layers. The observer is a structured pattern that emerges within the layer, looking at other patterns within the same layer, and possibly making inferences about the layer below. You and I, sitting here thinking about quantum field theory, are patterns at the macroscopic layer. The neurons firing in our brains are patterns at the chemical layer. The molecules making up the neurons are patterns at the quantum mechanical layer. We are not standing outside the system. We are inside it, all the way down. There is no privileged outside view. There is no place to stand from which to see all the layers at once. Every measurement, every experiment, every theoretical insight happens from within some layer. We cannot step into a metaphysical observation deck and look at reality whole. This is sobering. It is also, in a strange way, kind of liberating because it explains why physics has the texture it does. It suggests that physics, even at its most ambitious, is always going to be an internal map, drawn from inside the territory it is trying to describe. The unification of all forces, if it is ever achieved, will be an internal unification, achieved by patterns inside the system describing other patterns inside the system. The discovery of the deepest layer, if there is one, will happen from within whatever layer we currently inhabit. We will never be able to step outside reality and see it in some external way. We are part of the system. The system is what we have access to, and our descriptions of it, no matter how accurate, are descriptions from within. That does not make the descriptions any less true. I want to be careful here, because this point gets misunderstood a lot. Saying that physics is an internal map does not mean physics is fake, or arbitrary, or culturally constructed in some loose sense. The descriptions are true. They are true in the sense that they accurately predict observations, that they capture real regularities, that they let us build technologies and reach distant planets and split atoms. But it changes what we mean by truth in a subtle way. Truth becomes a property of layers, not of some final external matching between description and reality. A description is true at its layer if it captures the regularities of that layer. The deeper question, whether any layer is the real one, the layer that exists most or counts most, or matches reality in some absolute sense, becomes harder to even formulate. The question may not have a meaningful answer. So if quantum field theory is a layer, and the layers go down some unknown distance, what does that mean for the human project of trying to understand the universe? It means the project never ends. There is always another layer to look for. There is always another approximation to refine, another set of regularities to map, another piece of structure to describe. The dream of a final theory, a theory of everything that closes the book on physics, becomes harder to take literally. The universe might not have a bottom. There might just be layers all the way down, in a regress that has no natural stopping point. Or if there is a bottom, it might be permanently inaccessible to us, hidden behind energy scales we can never reach with any conceivable technology, or behind logical gaps we can never bridge with any conceivable mathematics. Physics, in this view, is not a march toward a finish line. There is no finish line. There is only the steady, patient process of building ever more refined maps of a territory whose limits we cannot see. And here is where I want to get a little personal for a moment, because I think this part actually matters more than the metaphysics. The joy of physics, the real reason people spend their lives doing it, is in the building of the maps themselves, not in finishing them, not in arriving at some ultimate answer that closes the conversation. Each new layer is its own discovery. Each new consistency, each new refinement, each new piece of the puzzle that snaps into place is a window into a part of reality that no human being before us has ever seen as clearly. We may not reach the bottom. We may never even know whether there is one. But the journey down, layer by layer, insight by insight, is itself the point. And honestly, when I sit with that, The lack of a final answer stops feeling like a failure and starts feeling like an invitation. The universe is bigger than any final theory could capture, and that somehow is the most reassuring thing of all. Part 19, the final paradox. We have reached the place we set out for at the beginning of this whole conversation. Take a breath with me here, because what we are about to look at is not just a summary. It is the actual shape of the contradiction that modern physics is asking us to accept. Quantum field theory is the most precise framework in the history of science, producing predictions accurate to 12 decimal places, confirmed by experiment after experiment over decades of increasingly sophisticated tests, never falsified by any direct measurement in any energy range we can currently access. Every collider we have ever built, every precision experiment we have ever conducted, every measurement of the electron, the muon, the photon, the W and Z bosons, the Higgs. All of them have agreed with the theory, sometimes to absurd levels of accuracy, sometimes only after years of refining the calculations and the measurements, until the two sides finally met in the middle. The track record is essentially unblemished within the regime where we have been able to test it. It is also a framework whose mathematical foundation includes a theorem, proven 70 years ago and never overturned, demonstrating that its standard formulation of interactions is technically inconsistent. Hegg's theorem still sits there, patiently undermining the formal legitimacy of the techniques we use every single day in physics labs around the world. The theory depends on a perturbation series that diverges if you take it too seriously, that gives sensible answers only when truncated at the right point, and that turns to nonsense if you keep going past that point. Its renormalization procedure, the heart of the whole calculational machinery, was called a shell game and hocus pocus by its own architect, the same Nobel laureate who built it and who never publicly retracted the criticism. Its prediction for the energy of the vacuum, applied straightforwardly, is wrong by 122 orders of magnitude, the largest theoretical error ever recorded in the history of human science. Its mathematical foundation includes an open $1 million problem that has resisted solution for over a quarter century, and the people who would most like to solve it, the mathematical physicists who specialize in exactly this question, have made very little visible progress. Both of these things are true at the same time. I want you to really hold them in your head together for a second, because the cognitive dissonance is the whole point. Perfect predictions and broken foundations, empirical triumph and mathematical incompleteness, the most successful theory in the history of human thought and the most clearly unfinished one. The most accurate description of the universe ever produced, sitting on a base that mathematicians cannot fully verify and that physicists openly admit is provisional. This is the paradox we set out to face when we started this video, several thousand words and many layers ago. And it is the paradox we now have to live with, because I do not have a magic resolution to hand you. Nobody does. What we do have is a way of making the paradox cohere, and that is the resolution we have spent the last several parts arriving at. The layered reality interpretation. It dissolves the contradiction without making it go away, which is a strange thing for a resolution to do, but it is the most honest one available. The successes of quantum field theory are explained by the theory being a well-calibrated effective layer, with symmetry constraints so strong that they essentially fix the form of the predictions at the scales where the theory operates, almost regardless of what is happening below. The deeper physics is washed out by the layering. The surface predictions come out right because the symmetries leave very little room for them to come out any other way, and the theory is built around respecting exactly those symmetries. The failures are explained by the theory being only that, only a layer, with deeper physics required to handle the regimes where the layer breaks down. The cosmological constant problem becomes a signal of the deeper layer, a place where the surface description cannot account for what is happening, because the underlying structure is doing the heavy lifting. The renormalization mystery becomes a feature of how layered descriptions work, a natural consequence of integrating out high-energy physics you do not have direct access to rather than a defect in the formalism. The asymptotic series becomes a property of perturbation theory in any effective description, not a unique flaw in this particular one. The whole picture starts to make sense as soon as you stop expecting quantum field theory to be the final word and start treating it as the most accurate intermediate description we have ever managed to construct. But notice what this resolution cost us, and I want you to feel the weight of this, because it is the part that physicists themselves often have a hard time saying out loud. It costs us the dream of completion. It costs us the idea, dear to physics for centuries, that we are converging toward a final theory that closes the book on reality. For most of the 20th century, the project of fundamental physics had a clear endpoint in mind. Find the theory of everything. Write down the equation that explains every other equation. Reach the bottom of the explanatory ladder and stand there, finally finished. The layered interpretation says that endpoint may not exist, or if it does, we may not be able to get there from here. The more we understand, the more we realize that what we know is a layer. The more confident we become in our predictions, the less confident we can be that our predictions describe the deeper structure of nature, because the very precision that makes us confident is precisely the precision you would expect from a well-calibrated effective theory, whose deeper workings are far away. Physics is not completing itself. Sit with that sentence for a moment. Physics is not completing itself. It is compressing reality more and more efficiently into effective descriptions whose underlying machinery remains hidden. Each new theoretical advance is a better compression, a more elegant summary, a tighter fit between symbol and observation. But the underlying structure those compressions are summarizing is not getting any closer to us. The success is not a sign that we are reaching the end. The success is a sign that we have built a very good interface to a part of nature whose deeper workings remain dark. We can interact with the interface. We can use the interface to predict, to build, to explore, to confirm. But the interface is still an interface. There is something on the other side of it. And the better the interface gets, the more we are reminded that there is still another side. We do not know what is on the other side. Let me say that plainly, because evasion on this point is one of the things that makes physics communication harder than it needs to be. We have hypotheses, we have candidates, we have mathematical guesses, but we have no direct experimental access to the deeper layer. We are reasoning from the surface, and the surface, frustratingly, is consistent with many possible underlying structures. Different hypothetical bottom layers all produce the same effective theory at the scales we can probe. That is part of what an effective description does. It compresses information. And compression is one way, in the sense that you can recover the surface from the depths, but you cannot uniquely recover the depths from the surface. That is why the candidates for what is underneath proliferate. Strings, loops, holography, causal sets, asymptotic safety. Each one is mathematically rich. Each one is consistent with current data. None of them have produced a decisive experimental signature. We cannot tell them apart from where we sit. Some physicists believe the deeper structure is fundamentally mathematical, that the universe at its base is some kind of pure mathematical object that gives rise to the physical world we experience as a sort of side effect of its internal logic. Others believe it is physical in some new way we have not yet learned how to describe, perhaps strings, perhaps networks of quantum information, perhaps something not yet imagined by any human mind. Others still believe the question is malformed, that there is no fact of the matter about what is at the bottom, and the layered structure is all there is to be said about the situation. We genuinely do not know, and we may not know for a very long time, maybe ever. That is not a comfortable thing to say at the end of a video about physics, but it is the most truthful thing I can offer you. So the final paradox of quantum field theory is not just that it is precise and broken at the same time. That is the surface paradox, the one we started with. The deeper paradox, the one we are leaving with, is that the more we understand the theory, the less we understand what is below it. The more we trust its surface predictions, the more aware we become that the surface is all we have direct contact with. The depths recede as we approach them. The clearer the map gets, the more obvious it becomes that the map is not the territory. Quantum field theory, in this final reading, is the most beautifully calibrated mystery in the history of human knowledge. It tells us exactly what nature does at the scales we can probe, with a precision that no other science can match. It is silent on why nature is the way it is, on what is producing the regularities it captures, on what lies beneath the symmetries that constrain its predictions. And it points, by the very texture of its silences, by the precise pattern of what it cannot explain, toward a depth we have not yet been able to reach. The silence itself is a kind of speaking. Part 20. Closing. The theory we cannot escape. We started this conversation with a number. Just one number, on its own, doing more work than almost any other number in the history of science. 12 decimal places of agreement between theory and experiment for a single property of a single particle. The electron's anomalous magnetic moment, measured and calculated, lining up across 12 digits past the decimal point. The width of the United States measured to within a single human hair. I keep coming back to that comparison because I do not think the human mind is really built to feel a number that precise. We do not have an intuition for it. We have to translate it into something we can picture, and even the picture barely contains the actual scale of the agreement. Imagine standing on the coast of Maine, looking west, and somehow being able to measure the distance to the coast of California so accurately that your only error, your worst-case discrepancy, was thinner than a strand of hair. That is the level at which quantum field theory tells the truth. We are ending the conversation with a different kind of number. 122 orders of magnitude of disagreement between theory and observation for the energy of empty space. The cosmological constant problem, the largest theoretical error ever recorded in any branch of science. A number so wrong that the theory predicts a universe that could not have produced us, sitting alongside a measurement of a universe that obviously did. The same theory produces both numbers, the same equations, the same symmetries, the same renormalization procedures, the same asymptotic series, the same machinery of fields and excitations and Feynman diagrams that work so beautifully for the electron, failing so spectacularly for the vacuum. Right by an absurd amount in some places, wrong by an even more absurd amount in others. And the gulf between those two outcomes is not a small thing. It is the entire shape of modern physics. In the space between those two numbers, between 12 decimal places and 122 orders of magnitude, lies the whole story of modern fundamental physics. Everything we have walked through, the renormalization controversy, the Yang-Mills problem, the Hague theorem, the asymptotic series, the cosmological constant catastrophe, the muon anomaly closing, the Higgs being found exactly where it was supposed to be, the Standard Model swallowing decades of experimental challenges without showing a crack. All of it sits in that gap, and the recognition, slowly and reluctantly emerging over the last several decades, is that the only way to make sense of both numbers at once is to stop thinking of quantum field theory as the final word about reality. Because no final theory should produce both of those numbers. A real bedrock of physics should be either right everywhere or wrong in clean, identifiable ways. Quantum field theory is neither, which is the strongest evidence we have that it is not the bedrock at all. It is not the final word. It is perhaps an extraordinarily eloquent middle word. I like that phrasing because it captures the strange status the theory actually has. Not nothing. Not everything. A description that captures something true about the world at a particular scale, with a particular precision, while standing on top of a structure it cannot directly see. The middle of a sentence whose beginning we do not know, and whose ending we have not yet read. Every experiment we run keeps confirming the description at its own level. The Higgs is found exactly where it was predicted. The muon anomaly closes after 20 years of holding open a possible doorway. The electron's magnetic moment matches calculation to 12 decimal places year after year, with both sides refining their numbers in lockstep. The Standard Model continues to absorb every challenge thrown at it by every accelerator and every precision experiment we have managed to build. And every philosophical and mathematical examination, every careful look under the hood, keeps revealing that the description, at its foundations, is not what a final theory should look like. The math is too unfinished. There are too many places where rigor is replaced by pragmatism, too many techniques whose justification is ultimately that they work rather than that they are mathematically sound. The cancellations are too miraculous. The way different contributions to physical observables happen to add up to small finite numbers, instead of the enormous values the individual pieces would suggest, looks less like a feature of fundamental physics and more like the fingerprint of a deeper structure quietly enforcing the cancellations from below. The vacuum is too suspiciously fine-tuned. The free parameters are too numerous and too unpredicted, with around 25 constants whose values are simply inserted into the theory by hand rather than derived from any deeper principle. The gravitational sector is too absent. The fact that we cannot include gravity in the same framework as the other forces, despite a century of trying, is itself a screaming clue that the framework is not the whole picture. So the theory keeps confirming itself empirically, while quietly admitting, in its own structure, that it is not the bottom. The data say yes, the math says wait. And we are sitting in the middle of that conversation, trying to figure out what to do with both messages at once. We are stuck on a layer, and from this layer we look down into a darkness that we cannot fully see into. That is not a poetic flourish. That is a literal description of the experimental situation. Our most powerful particle accelerator, the Large Hadron Collider, can probe energies up to around 14 trillion electron volts. The energy scale where quantum gravity is expected to become important, the Planck scale, is roughly 10 to the 16th times higher than that. To probe directly the scale where quantum field theory is expected to break down, and the deeper layer might become visible, we would need an accelerator the size of a galaxy. We are not going to build that accelerator, so we are reasoning from the surface, knowing the surface is not the bottom, hoping that something in the structure of the surface will tell us about the depths. Maybe one day, an experiment at some unimaginably high energy, or some unimaginably precise low energy probe, will lift the veil and reveal the structure underneath. Maybe a cosmological observation will finally pin down the cosmological constant in a way that cannot be explained without invoking new physics. Maybe a precision measurement of some subtle effect will catch the deeper layer leaking through. Maybe one day, a new mathematical framework will achieve what string theory and loop quantum gravity have so far failed to do, and produce testable predictions that take us decisively below the quantum field layer. Maybe the deeper structure is something we have not yet imagined, something that will make the question we're asking right now look as quaint as the medieval question of how many crystal spheres carry the planets across the sky. 500 years from now, our descendants might look back at our anguished debates about renormalization and the cosmological constant and smile at how we missed the obvious answer. Or they might still be wrestling with the same problem, having found that it goes deeper than we suspected. Or maybe we never reach the bottom. Maybe the bottom does not exist. Maybe reality is layered without end, and every layer we discover is just another approximation of an even deeper one, with the regress continuing forever, no final structure, no ultimate furniture, only an infinite sequence of effective descriptions. Maybe the search for the final theory is not a search for an answer at all, but a description of an activity, and the activity itself is what physics actually is. The journey, not the destination. The map-making, not the arrival. I genuinely do not know which of these possibilities is true. Nobody does. Anyone who tells you they do is selling something. But I think it is worth ending on this thought. The most successful theory in the history of human thought is also, by its own internal evidence, an incomplete one. Its precision is not a sign of finality. Its beauty is not a sign of bottom. Its agreement with experiment is not a sign that we have arrived at the end of the road. It is a sign that we have built something that works extraordinarily well within its domain, and that there is more, much more to be found below. We are explorers on a beach, mapping the patterns of waves with extraordinary precision, charting every ripple and every interference pattern and every curl of foam, while underneath us lies an ocean we have only begun to suspect exists. The waves are real. The patterns we map in them are real. But the waves are not the ocean. They are the surface where the ocean meets the air, and underneath them is a depth we cannot see directly from the shore. Quantum field theory is the wave map. The ocean is whatever is underneath. And the strangest, most beautiful realization of modern physics is that the wave map itself, in the very precision with which it describes the surface, is silently telling us about the depths. The texture of the patterns, the regularities, the cancellations, the suspicious cleanness of certain calculations and the catastrophic failure of others, all of it is information about what is below. We just have not yet learned how to read all of it. The story of physics, then, is not a story of reaching final answers. It is a story of recognizing that every answer we find is part of a larger question we have not yet learned how to ask. Quantum field theory is the most precise and complete description of reality ever constructed, and until something better comes along, it will remain the layer we cannot escape, even as it whispers, in the very structure of its equations, that there is something else, something deeper, something waiting underneath. We will keep looking, we will keep building experiments, designing detectors, refining calculations, proposing frameworks, testing predictions. We will keep refining the theory and refining the layers above and below, and we will keep wondering, in the late hours when the math gets quiet and the data sits still on our screens, what exactly is hiding beneath the most successful theory in the history of human thought? Maybe we will find out, maybe we will not. But the question is the most interesting one we have ever managed to formulate, and tonight you and I sat with it together, in the quiet, and that, in some small way, is part of the search. The wondering itself is part of the work. Until next time, keep looking up, keep looking down, and keep wondering what reality really is, all the way down to whatever bottom it may or may not have.